Okay, two events A and B are such that the probability of A is 0.33, probability of B is 0.45, and the probability of A intersection B is 0.13. Find the probability of A union B, so the probability that either A or B exists. So this mightn't be any harm to remind ourselves that the union is or, the intersection is and. So the intersection is always more specific. Like it's like saying, do you play hurling and football? You have to play both to be in that group. Whereas if I said, stand over here if you play hurling or football, well, then we'd have a larger group because you can stand there whether you play one of them or both of them. So it includes a lot more people. Anyway, for this particular question, we are going to draw our Venn diagram. Now, we only have two sets. So we have A and B, labeled A, B. I know the probability of A. So the probability of the universal set has to be 1 because that's the highest probability can be. So the probability of A is 0.33 and the probability of B is 0.45. We're told that the intersection is 0.13. So all we have to do is take away the 0.13 from the 0.33 to get the A only, the moon shape here, the A only. So that's 0.2. Then after we do that, we do the same over here. We take the 0.13 away from 0.45, and that gives us 0.32. Now, when I add this, and this together, I get 0.65. So that leaves 0.35 on the outside. So that's my Venn diagram done. Now to answer the question, it's the probability of A union B. So all I do is do the union. So I add 3 of these together. And my answer, as I said, is the 0.65. Okay. Find the conditional probability of A complement given B complement. So what we need to do here is we write the formula for our conditional. So we do the probability of A complement intersection B complement all over the probability of B complement. So that's the formula we would have used in class. So now it's just a case of filling it in. So I put in my intersection, my 0. Oh no, sorry, yeah, it's the intersection of the complement, sorry. So actually what I might do is get the highlighter here. So if I am looking for the complement of A is everything but A, basically. So A complement is everywhere I have the yellow highlighter. Now, for B complement, let's do blue, for example. So B complement is everything outside of B. And that would be including that section there. Now, if I'm looking for the intersection, I'm basically looking for the section that's green because the green section is where the overlap is happening, where the yellow and the blue are overlapping. So there's only blue there, so that's not included. This one isn't included for either of them. The yellow is obviously not included, but you can see that this entire outside section is green. So that's my 0.35. So the highlighter has really helped there if you find that hard to imagine, I suppose, without using them. And then the probability of B complement is everything outside B. So essentially we're saying, okay, B itself is 0.13 and 0.32, or as it said up here, 0.45. So B complement is basically everything outside of that. So we have 0.55. So when we divide that in, we get 0.63 recurring. Okay, and that is our probability in that case. State whether A and B are independent and justify your answer. So we had a formula that we use for independent. So if you want to test if something's independent, what you're really doing is seeing if the intersection is the same thing as the probability of each multiplied. So the probability of A, we said, was 0.33. So I'm just using the formula. The probability of B is 0.45. And if I multiply them together, I get 0.1485. But the probability of the intersection is 0.13. So we can easily see now that they are not equal. Now, if they are not equal, therefore they're not independent. So that is our method for proving whether it is or whether it isn't independent. So we've used two formulas there really in those last two sections. So we'll just highlight them. So with this one over here for conditional, and this one here to decide if something is independent or not. Okay, and then we had, so there was another set then joined in. So we now have this event C, and the probability of C is 0.2. A and C are mutually exclusive. Now that means they can't happen at the same time. So that means there is no intersection between them. So in this case, there is no intersection between A and C. While B and C are independent. Now, B and C are independent. That doesn't mean it doesn't have an intersection. In fact, it usually does. It just means that one has no influence on the other. I think the example we used in class is it's raining outside and you get, a H1 in your maths exam. They're independent. One does not have a bearing on the other. So, okay, so in this case, I'm going to have to draw three circles because I have three sets now. I have the A and the B that I originally had, and I have the C now, A, B, C. So I know the probability of C is 0.2. Looking back on the first question, my A was 0.33 and my B was 0.45. Okay, so that doesn't change. Now, it says A and C are mutually exclusive. So if they're mutually exclusive, this section has to be empty. So I'm going to cross that out entirely. They have nothing in common. There is no intersection. So that area is blank. Okay, that's something we know. Now, we know that A, B, and C are independent. Now, that formula we used earlier, if they are independent, then the intersection between B and C should be the same as the probability of B multiplied by the probability of C. So that's the same formula we just used in the last part. Now, we don't know the intersection of B and C, but we do know the probability of B, and we do know the probability of C. So we end up finding out what the intersection is between B and C, 0.09, when I multiply them. So I can fill that in. Now all I have to do is take 0.09 away from 0.2, which is 0.11. I take 0.09 away from 0.45. Actually, sorry, this is still 0.13. Isn't that what we had earlier? Yep. So the A doesn't change. There's nothing really happening there, but the B does because B now has the 0.09 as well. So that leaves 0.23 in that section, B only section. So that's the diagram finished. And then the last question says, find the probability of B union C complement, the probability that neither B nor C occurs. Now, again, highlighters are handy here, I think, so I'll get my green highlighter. B union C complement basically means everything except for B and C. So what is everything except for B and C? Well, we go around here, everything outside the circles except for B and C. So essentially, we have just really the 0.2. So the 0.2 from here, the 0.2 from here. No, sorry, that's part of C. Sorry, we haven't worked that out yet. So what I'll need to find out is the outside. So we'll just quickly work that out because, yeah, we don't have what's outside the circle. So I'm just going to add up, see what all of this is. 0.2 plus 0.13 plus 0.23 plus 0.09 plus 0.11. Now, when I add up all of them, whatever is left, remember it has to add to 1, is going to be the outside. So 0.2, 0.13, I'm just popping this into the calculator, 0.11. Okay, so that's giving me 0.76. Now, if I have 0.76 and I take that away from 1, that leaves me with 0.24. But I do have that section as well up there, the 0.2. So my final answer is combining the 0.2 and 0.24, which gives me 0.44, and that's my final answer. So that green section is the A only, and then everything outside. Okay, so that's it for that one.